Thank you again for joining us for this webinar this afternoon on Simcenter Reduced Order Modeling. I'm your host, Scott Tebow from ATA Engineering, and we are pleased and proud to have with us our guest speaker, Darren Nunes from Siemens Digital Industries Software. Before we launch into the webinar proper, I'd first like to say a few words about our host, ATA Engineering. ATA Engineering provides high-value engineering services to our customers in a variety of industries, especially aerospace and defense, but also spacecraft, industrial mining equipment, high-speed systems such as hypersonics, and even in themed entertainment, if you think roller coasters, animatronic figures, and other types of attractions. ATA Engineering is an employee-owned small business with a full-time staff of over 200. We specialize in design, analysis, and test from our offices nationwide. On the Siemens side, we are a Siemens expert partner, a platinum-level solution partner for Siemens Digital Industries Software, specializing in simulation. So the Simcenter product line is the center of our Siemens world, and that includes products such as Simcenter Reduced Order Modeling, Simcenter 3D, FEMAP, Nastran, Star CCM+, HEEDS, AIMSIM, and the full line of Siemens test and measurement solutions, for which we are the exclusive channel partner for Siemens. We also provide licensing and support for Teamcenter, NX CAD, and CAM, and we do this through our hotline support available 8 a.m. to 8 p.m. Eastern Time, and through software and implementation services, and through training and training materials. In fact, ATA Engineering quite literally wrote the book on Nastran, and all training materials used by Siemens worldwide for Nastran users are developed under contract by ATA Engineering. If you'd like a whole bunch of free resources, there is an abundance available on our website, ata-e.com/software, where you can download white papers, recordings of previous webinars, tips, tricks, and a whole lot more. We hope that you visit. And now I'd like to introduce our guest speaker, Darren Nunes. Darren is a Siemens Simcenter Solutions consultant for Siemens, and he provides design and analysis support for all kinds of advanced simulation projects. And we're pleased to have him here this afternoon to talk to us about this new product, Simcenter Reduced Order Modeling.
Great. Thanks, Scott. Thank you, everyone, for joining. So today, as mentioned previously, we're going to be talking about reduced order modeling, how it can be incorporated possibly in your current workflow, as well as what we can offer from a Siemens Digital Industries software standpoint. So quick kind of agenda workflow. My plan here is to have a basic workflow of reduced order modeling introduction, then go into kind of a product overview of Simcenter Reduced Order Modeling, how it's incorporated into our portfolio, give some more hands-on demo type examples that we've done that I've worked on personally, open up some of the software, hopefully if we have time, then go maybe a little bit high level with some application examples on incorporating different tool sets, different integrations of simulation data or test data. This was a recent release here, so 2310 has some newer features that I would like to just point out, and then conclude with just an overall summary of why Simcenter Reduced Order Modeling is something that could probably improve your workflow and process. All right, so an introduction, right? If you maybe haven't heard of reduced order modeling before, what is it, right? So the definition is really getting a simplified model from a complex system. So what that means is, there's a whole bunch of variables that are, say, if you're doing a simulation, there's differential equations being calculated in the background. If you're meshing, there's a whole bunch of calculations of variables that are defining really the way that simulation is getting its data or output. But the key factor with reduced order modeling is we're keeping that complexity, right? So that full order model, right, which you see there on the bottom, but all we're doing is we're speeding it up, right? We're simplifying it, we're analyzing it, and the way we're doing that is through model order reduction techniques. Now, model order reduction techniques aren't something new. It started really in the 50s, really with Laplace transforms, model order reduction. There was something called truncated balance realization in 1981. We had some decomposition or ways that Surovich also had performed some control theory with his methods, and it really was a way of leveraging computation power as it was developed over the years, but leveraging processes to use for the buzzwords, right? The AI, the machine learning, right? So in the machine learning, right, there's regenerative learning, there's something called large network learning. There is different algorithms and outputs that you see, right? So on the left-hand side are just some techniques that people use to develop, different softwares, different off-the-shelf tool sets, different algorithms, neural networks, Gaussian processes. And these are ways that you're taking that engineering or science data and have this data-driven modeling occur, which is ultimately analyzing this complex system to develop these faster, effective models, for instance, right? So the research really has been done, but Siemens as an organization has understood that there's no one off-the-shelf reduced order modeling technique, right? This table summarizes what Simcenter Reduced Order Modeling offers. And what I mean by that is it could be a neural network algorithm that really has multi-layers to it. It has different neurons. Those layers have different densities, different activations. And you don't have to be an expert in this tool set, right, or in these algorithms to be able to perform the process of model order reduction. It's kind of a click, drag and drop, and that's the point of using a off-the-shelf tool. Siemens as an organization has used expertise and different knowledge base to not only develop these algorithms, but been able to have the openness to link it not only in the Simcenter portfolio, but in a larger tool set of data. Neural network is one machine learning algorithm. There's other ways of mapping or looking at machine learning or data-driven analysis. So there's RSMs, response service models, there's autoregressive type modeling, there's something called Kriging, there's a Gaussian process, we can do polynomial regressions. And as we see on the bottom, there's different data sources, right? So we have a system simulation tool inside of the Simcenter portfolio called AIMSIM. That's where you can consider kind of the 1D type space where you're building differential equations with connecting up different components together, and might already look as a simplified way to going from a complex 3D or CFD type analysis where you're doing computational fluid dynamics that is really highly intensive on the computer, right? So that whole CPU time. So really, what are the benefits, right? So the main approaches is we want to keep this high complex model. We want to keep the fidelity, and you do that through those model order reductions that I just talked about. And what that really is going to do, it's going to preserve those behaviors. It's going to preserve all the outputs that you get for certain boundary conditions or input conditions, but it's going to give you a lot more CPU functionality. So you'll see, let's say, hours or days worth of CFD run simulation or testing of data that you can run really a neural network or other levels of algorithms on this data set and have it train and now run from, let's say, 15 minutes, 30 minutes, over an hour to milliseconds, right? So you're talking thousands of times faster to be able to incorporate not only the complexity of it, but incorporate a more efficient type simulation because you're running that simulation quite fast. Okay. So what does us as an organization offer in the Simcenter portfolio? There's this new release, and there was a previous release of something called Simcenter ROM Builder. It's now Simcenter Reduced Order Modeling. So it's a completely standalone product that really incorporates this problem, right? The problem, maybe your simulations are too slow. Maybe we want the CFD group to work with the 3D mechanical group. Maybe we have someone developing controls algorithm. Someone else is working on a systems level model, and we can, link those all together through, yes, interfacing FMI type functionality, but maybe those simulations are too slow and we can't get them to work together, right? Maybe we want to deploy our simulations on real time, and the only way to reduce that down and get it to run fast enough is through model order reduction and creating a reduced order model itself, right? And as some of us may or may not know, experimental data is rarely ever overlapped when it comes to simulation standpoint, right? So we're really trying to take this shift left problem of being too slow and use them more early on in the process without minimizing that complication of times, right? So we know that you can shift everything right and have these digital twin type philosophies past the design space, but really look at what's compatible. How can we get this closed loop type functionality? There's something called executable digital twin that reaches out to a multitude of persona, right? So if you're a simulation engineer, you're a test engineer, you're a controls engineer, we can get this digital and physical world intertwined to really get this efficient way of modeling and simulating together in a common environment or through a synergy. Now, if you look kind of where this is, or a better way of viewing it is we're combining physical testing, simulation data. That simulation data might be CFD data, systems level data, basic calculation data, and we want to combine them, but we want them to be deployable, and we want maybe to speed up our CFD or 3D level simulations. You can combine all those together in this one tool set, and you can run one algorithm on it or multiple algorithms to get this, non-siloed approach with a reduced order model. And what that is going to do is it's catalyzing digital twins. So it's taking your physical hardware, your physical test bench, and having the ability to replicate it in digital twin without having to do any level of mathematics or calculation. All you're doing with a simple clicks, you're defining what your inputs and outputs are and running a calculation to get what we have considered a digital twin that can be used in multiple tool sets. There's something called executable digital twin. That's really to get things running real time. We have something called Insights. It's part of our portfolio that gets you the ability to run simulations real time, but you can even have level of control algorithms, alter or state machines that really are looking at data real time and combining that with simulation to get what we call an executable digital twin to make real time analysis. And the solution is tool agnostic. So what it means is I can take data from other tool sets, maybe outside of our Simcenter portfolio or from our testing solutions, and really leverage them inside of this standalone tool. Right. So as said before, we want to reduce these models to get them to run faster, but we want to leverage both our data sets from simulation and test. And we can deploy those not only internally, externally, depending upon the packages and solutions you buy, right? And we know, maybe we're looking at industrial edge, or maybe we have some virtual sensing in the clouds. The benefit here is we're really getting this one-stop shop for reduced order modeling. You're not going in and becoming a reduced order modeling expert. You're not coding, right? And it's tool neutral. So you're really defining and keeping your design IP by getting this, let's say, solver-free model. And what that means is you're deploying an FMI or an Onyx file, which you'll see here in a second, and it was just data that was learned upon, and you can go and export it and import it into whatever tool set you want. So what I mean by that is we saw there's different datas, right? We have static data, we have dynamic data, that will also ultimately define your reduced order model technique. But you can take data from our Simcenter portfolio. So you see there that Simcenter AIM-Sim, that's our system level tool. There's HEEDS, which is a design exploration tool that's also tool agnostic, and you can kind of link in a whole bunch of tool sets or workflows or data intertwined with that. We have our test lab solution, our Star CCM, which is a CFD level solution. If your simulation data is able to export a CSV file, we can use that. MATLAB file, maybe you have a matrix. And what you do is with a simple click of a button, you open a new project, and you'll see in these demonstrations, you open a new project, you import that data, you define what your inputs and outputs are, and based on your level of expertise of reduced order modeling, and there are different wizards and apps embedded underneath, but based on your type of data, you're running a technique, right? So if you have time series or static samples, maybe you're doing an RSM, maybe you're doing a static neural network, If it's a state space, maybe we're looking at, some level of an automatic creel off. Maybe we're having some dynamic time series data where we're doing a dynamic neural network rather than a static neural network. Maybe we have some auto-regression functionality. Maybe we're getting 2D fields from CFD or from an FEA level analysis. The tool will choose that for you, or you can define it yourself based on where you are in the reduced order modeling technique or world itself. So I always say that the best way to learn is truly from visualization or hands-on. So I'm going to go through a bunch of examples here that I've done. I worked with product development on. These first 4 are going to be in our newer tool set that I helped develop with product management on some different functionalities, right? And based on different types of data. So the first one here, right, is looking at a flapper valve, right? So we had different CFD runs, and you go into the tool, you click static samples, and now we add data. So you select the data you're going to train on, the data you're going to validate on, and let me just go back here, right? So we selected, and they had specific aliases to them, and in that imported data, it'll automatically define and know what the columns are, right? So if you had inlet pressures, valve openings, and again, this is exported from our tool set of CFD from Star CCM, but you can get it from any other levels of tool sets as well. Now, when we define, we then have to assign those data sets, right? So you see these models or data plotted, right? And they know that there's common variables. We have to train on one and validate on one. Now you can have more than 2 sets of data here. You can train on multiple ones, which you'll see that I've done, right? You can validate on more than some as well. But after that, we start ultimately our sweep, right? So you're seeing the different variables plotted here, and we can go to a correlation plot. So this is similar of how these valves, forces, pressures are correlating to one another, right? And then you can dig deep into the results later on once we complete that process of machine learning, right? So in this instance, we're going to select a model sweep. So what's great about a model sweep is all you do is you define, oh, let me accidentally clicked out there. So you'll see you go in, oh, I think I might have gone past one. Sorry. So we are here, right? And we define what our inputs and outputs are going to be, right? So if we know that our pressure and valve opening are going to be our various inputs, the outputs we got were flow rates, forces, pressure drops, right? We can now, with a simple click of play, you're going to see this train real time, right? So this is real time running, and it tells you how well it was able to train on, right? And it tells you what processes are the best. So it tells you, if you see here, 99.1% training fidelity of using the Gaussian process, and it validated at roughly 97%. The second one, again, also used Gaussian process. As I said before, based on the data, and this was a model sweep, you're not defining what model order reduction technique is being used. It will automatically do that for you, okay? So you see how well it was able to correlate with that data, train on that data, validate, as I said before, and it gives you the different color coding to really show. So if you see the samples and how well it evaluated, right? So XY plots, you can get different plots of your outputs of your data as well, and then you can save it, right? So you save it locally, or you save wherever you are, and then you can run through the process of exporting. So there's a great comparison here. If we click this open, and just based on time, I'd much rather show a lot of the demos here, but you're seeing how well the fidelity was able to match and beat, match and validate to those different data sets. And this was from a static CFD, from a flapper valve CFD. Now, these are our export options. So you see we can export FMU 2.0 co-simulation, right? Or model exchange. We can do an S function. We can also do it as a aimsim model. So some of the demonstrations you'll see it was easier to validate and rerun and show the benefits of reduced order modeling, just bring it into our AimSim tool set, because it's not only part of the Simcenter portfolio, but it's fully FMI and FMU compatible. If we were, and this is a Gaussian process, if we were doing a neural network, we can also export it as an ONNX file. So that's an open neural network exchange file. There's other ASCII files and tables. So if you were doing any level of, Python scripting or scripting afterwards to the model, we can use those exports as well. Okay. And once you export it, you see it'll tell you that it validated and exported, and then you can use it in another tool set. The next one here is a time series data. So using the neural network, right? So this was an oscillator, and this is the wizard I was talking about. So with a simple click of a button, you can say, hey, we know that the inputs are force, we're going to get velocity and displacement, and we're going to run specifically a neural network. We know that it's going to be complex dynamics, right? The model complexity is simple, and we don't change anything. You see here, there's a specific density layer as default, right? After using the wizard, it then alters it. So it's now changing it to an RNN. It's changing that one layer to have 10 cells, it was 3, and now it has a reluctant activation. So from there, you can apply another template. So if I said it was medium complexity, now there's, as you see, a density layer, an RNN, and there was another layer added. So it tells you the training loss. You'll see how well it was able to be trained on. This is just zooming in. So you see that neural network is the yellow line, and that was how well it was ultimately, I'll pause it here. That was how well it was able to train and validate based on the displacement. Right. So you see here, the fidelity on velocity was roughly 96.8%. The training fidelity on displacement was 97.18. Okay. So that's where we get the techniques and leveraging what the tool offers from just even an illustration standpoint, getting different complexities, and not being an expert in neural network development or in those algorithms, and just simply importing data, knowing what your inputs and outputs are, and defining and letting the tool use the wizard itself. Okay. Next one, right? So this is 2 transient CFD runs of a bus bar. We're capturing different temperatures and seeing over time different heat transfer coefficients, right? How the coolant temperature is changing, right? How that current is changing, and the data is going to be in a CSV file, right? So we started a time series project. We imported those 2 files, which you see here, right? And you can plot them. These are the different temperature sensors that we had across that bus bar, right? You can toggle showing all of them, some of them, based on whatever you're looking for. We know the first one was a training, second one we're going to validate on, and we knew that we wanted to use a neural network based on the type of data we were using with CFD. So again, defining what the inputs and outputs are, we knew all of those temperature readings were going to be outputs. This was a medium complexity, so you see it automatically defining and looking at the data, how much data is provided, and this one is a little bit different than the last one, right? Density layer, first one's 15 cells, same activation. Next one, RNN, with 18 number of cells, similar activation as well. You can go in and change it if you personally know better activation. So epochs is how many times it's going to iterate and run that process of that neural network. So this one, based on the data, we ran 60, and this is sped up a little bit, but we're not talking a very, very, very long time to train on this data. So again, you can see the training losses that is plotted here, and how well it was able to keep the fidelity of those dynamics, right? So you're seeing the comparisons of the temperatures versus that neural network that was created, the temperature, the training data versus the validated data as well. Okay. Again, one simple click of a button, export. We exported a neural network. So as you see here, that ONNX file is now able to be selected, as well as FMU, S function, and an AimSim model. Okay, so here's bring it back into AimSim. Okay, what's great is now you have a component, dragging and dropping it in. You're selecting it. So we had the data from the CFD. So this CFD was flow EFD. We're demuxing it. We're running it as the various inputs across our simulation, and you see 3,000 seconds of simulation, and how well we were able to validate exactly the same as you saw in that reduced order modeling tool set. Okay. Last one here, we had a thermal vehicle comfort. So a lot more advancements going on in the CFD 2D fields type functionality, okay, where we're looking at, this was files generated from star CCM of thermal comfort. So we had 8 different configurations. The cabin was heated up in 3 different scenes, right? So we have these different snapshots, and its auto tagging functionality or capability allows us to see what training data and how well and how we want to interpolate. So you define those inputs and outputs. Again, you go through that training process. And this one takes a little bit longer since it is using images and that start data, but it will tell you how well we can get our good fidelity, right? The green versus the reds. Okay, we could have trained this a little bit more, but based on just the evaluation. And what's great is we now have a slider based on the inputs and parameter sets that we ran through for our simulations. You have this drag and drop, this slider to be able to adjust heater seats, those 3 locations that we adjusted temperature, and you see from a visual standpoint, where we're getting interpolation of that field in that prediction. Okay. We can always export this as well and use that CSV file in another tool set for different post-processing based on whatever tool you're using. Okay. So the exact same workflow happened. Okay, I did similar workflows with other colleagues, other customers, and had different data that I could use. So the first one I used kind of high frequency data. It was engine data. We were trying to get engine mapping. So you go through that same process, right? You're defining what your inputs, your outputs are going to be. And I was able to also run that model sweep capability where you see it ran static neural networks, static Gaussian processes, and you have your training and validation fidelities. What's really awesome is in this comparison, we can see how many times it trained on it, how many layers it created, what the different layers types were. If you were a ROM expert or you're in the process of wanting to learn more of neural networks or Gaussian processes, it will tell you, even on the bottom, it'll tell you the different training methods, even from the Gaussian process or the RSMs, right? So the color coding is all based on how well it was able to fit to the data as well. So what's really awesome, as I said before, right, this was lots and lots and lots of high frequency test data. We then can bring it back into an AIM-Sim and run it quite quickly. So if you all can see the screen here, right, here's an engine model with that component that you kind of saw. This was 20, a couple days worth of running of high frequency test data. It took a total of elapsed time of 7 milliseconds to run a simulation. I just put static values in there, right? So we had a RPM, loading, Spark Advance, AFR. So you in the AIM-Sim tool, you can just drag and drop and we can plot all of our outputs, right? They're just static outputs because we just have, not default, but we have just a constant value. So there's no varying, but we're able to run, days and days and get a digital twin of our training data, or sorry, of our testing data to then train it on and get it through that neural network using a model sweep. Okay. The next one, right, is an ATR example of CFD level simulation. So as we know, right, through the process of CFD, there's a lot of things involved, right? We're developing CAD, we're developing ways that those CAD are going to integrate together. So this really was just from one simulation on just a basic laptop was taking roughly 90 minutes. So about an hour and a half, right? There was a whole bunch of iterations to converge. And what did we do? Well, we said, hey, let's go through a design of experiments inside of this CFD and let's train on it, right? And this was a user who's never done anything involving reduced order modeling. He's never used or developed any techniques of his own. So he was a CFD expert and I worked him through this process, right? So we knew we were going to use environment pressures, temperatures. We had some fan curves. We had different heat transfer coefficients or temperatures, and we wanted to get the outputs of different temperatures, but as well as mass flow rate. So in the definition of the CFD, we did varying of input variables, right, of that ambient pressure or of that temperature, of those walls, of those heat transfer coefficients. and we knew all the temperatures and flow rates that we had as outputs. So you see, this was a whole bunch of results of data that we got from all of these simulations. Well, simple click of a button, now we're able to input all of those CSV files and define what we knew and what we had for our inputs, what we had for our outputs, right? The different chips involved on the different CAD geometries that we had run in our CFD. So if you see from here, right, we were able to get almost 100% training fidelity. We got 99.825 training fidelity using a neural network, right? And he took the time of just changing some of these layers, changing some of the activations to get it to this value, right? He didn't go in and change any algorithms, but what was really amazing is he used this tool-agnostic simulation tool without having to know anything about reduced order modeling, without having to find any level of expertise of developing these calculations. He let the training method and everything else be defined by the tool itself. So you see, it was a 98.7, it's almost a 99 validation fidelity, with then taking this data point and then comparing and validating it back into AimSim was, again, the tool that was the most robust and easiest to export it to, since it was a neural network. So we had that specific component we can drag and drop. And if you see on the left-hand side, those red components, those are just all of the inputs that we used in the CFD models, right? And we were able to then, if you see on the bottom, get this level of comparison from that data point. So how does that work, right? If we were to see here, this ATR example, that neural network that you saw, right, has all of those inputs we trained on, and then we have all of these temperature outputs, right? So if I select this neural network, right, okay, we're getting all of the data outputs, flow rates that we can get. And I think I unfortunately had some issues connecting this data set, but you're going to get, like you saw before, the ability to get that transient data with a fast running simulation. Okay. Another one that was used still in kind of the electronic space was a server rack. We had someone, they were simulation engineers, but they weren't controller engineers, right? They didn't have the expertise of PID level integration or how they wanted to incorporate into their process. So we had just a simple server that we took different power inputs through. We had different deratings of these fans, right? And we got different output temperatures on those different functionalities or different components, sorry. So we went through this Latin hypercube sampling, which is built in and embedded inside of Flowtherm. And we ran 200-second durations and ultimately got all of these outputs that we can train on, right? So we had the different validation training. You see the different data sets that we got out there. But if you see, this is it imported into our tool, right? So we had the derating of the fans, we had different powers of the fans, we got different output temperatures, but the main factor was wanting to get a digital twin from our CFD, have it run a lot faster, because we didn't really know how to develop the controls, and sometimes that can be very time intensive. So using and leveraging the ROM toolset, reduced order modeling, Simcenter Reduced Order Modeling, you'll see that we got a 93% training fidelity and roughly 88 or 87% validation on that data that we performed. And again, we could have gotten more temperatures, more power readings through. This was just a basic proof of concept that we done, and we performed in less than 24 hours. And it was quite amazing, right? And we were able to bring it back into AimSim and leverage and benefit the different apps of a different simulation tool. So in that system simulation tool, like AimSim, yes, it's multi-physics, multi-domain. We have a signals and controls library that has these embedded apps or PID tuning apps inside of them, right? So we dragged and dropped that neural network that we had as a component. And then if you see here, right, the elapsed time of the CPU was, again, in the 0.05, right? Or I think this was 0.045, right? So you're talking lots and lots and lots of CPU time that was used to develop and get these CFD runs, but able to get, and you see these controller set points that we have from that data set as well. Okay. And for the purposes of time, I'm just gonna stay in the presentation here rather than open up the AimSim tool again. Okay. So the last one, kind of for demos, is this AC loop. So this was an AIM-sim model that was developed that had a car cabin. We had an evaporator. We had different heat exchangers that were discretized. We had expansion valves, a compressor that was there. Sorry, condenser. We had even an integrated bottle. We then removed all of those components, right? We kept the fidelity and we got it down to this neural network that really was able to train and get the compressor and everything, the condenser, all of those mathematics embedded inside of it, and it was a neural network. So we ran these 5 different drive cycles, FTP, HW, FET, NEDC, SCO3, and the US06, and those were run inside of our AIM-Sim tool set, saved out, and then just imported through that data import inside of that Simcenter Reduced Order Modeling, right? We knew that our inputs were different variables of temperature, speed, whether that was the vehicle speed, compressor speed, different commands to move that compressor to go faster or slower, right? And we got some evaporated temperatures, relative humidity, and was able to get the outputs inside of that cabin or other locations. So if you see here, we did use that neural network based on the transients of the complexity, but we used the highly complex in the wizard, which defined 3 different layers, 3 different densities with the reluctant activation, and we only ran 100 epochs. Just, you know, again, a lot of these proof of concepts, or even with this learning process, is done on a basic laptop. But again, we're not talking about hours and hours and hours of training. This, I think, trained in less than 20 minutes, right? And we got such a high fidelity that I was like, oh, let's just use it in our tool set. But what's really great is you see not only from the CPU standpoint how well it was improved, but even the values of getting of matching, right? So the detailed model versus the actual cabin itself, right? Temperature of the cabins over those different drive cycles and how well it matched, right? The different colors. The detailed model is the blue, and if the red is that neural network. Okay, so it's pretty amazing how, you know, we got all of these CPU times to exponentially go faster, right? So the CPU time to run this first cycle was, you know, we're running a time, I think, of roughly 1200 seconds, right? Simulation of 1200 seconds long. The first one solved in 1.3 seconds, then 1.7 seconds, and then 1.3 seconds, and then 0.62 seconds, I think. And then this one was a little less than 1 second, right? So your CPU time is exponentially faster, but you're seeing the fidelity of the high system model that we had before, or the high data set of CFD, or the high testing data that we had, that we learned on, okay? And that's where we're really benefiting the most, is keeping that fidelity but speeding up that CPU for efficiency, okay? Now, there are a whole bunch of application examples that I'll reference. I don't know if there's enough time to specifically go in detail through all of them, but just wanting to everyone to have the understanding of where this reduced order modeling technique can be used in your current simulation platform. So if you were doing battery packs, right? So we have something called Battery Design Studio, BDS, in our Star CCM portfolio. We have these capabilities for detailed electrochemistry, or all of the different high depth analysis that we're getting in from that CFD. So the CFD run, we roughly had, I think each one was 2200 seconds long. We sped that up, so we looked at voltage, state of charge, you know, the heats coming off of the battery, so the thermals, and, you know, there's different aging functionality that we can get inside of our AIM-Sim tool set. But we also were able to see and validate and get different temperatures, high, lows, the averages. But we went from 2200 seconds to 40 milliseconds of data. So, you know, we were able to get a lot better controller integration because of how fast those simulations ran. And this really allowed us to get the system level analysis for, let's say, model in the loop or software in the loop type functionality. We know that in the process of all of these battery designs, right, safety is a main concern, performance is another one, lifetime. So allowing a faster run simulation rather than the 2200 seconds down to milliseconds, right? So that 55,000 times faster is definitely a way to be a lot more efficient. We can also use FEA. So you know, there's different methods that are used by the simulation. This one's, you know, the Krylov reduction, but you'll see we were able to take this 3D FEA model and get the real-time equivalent really for getting virtual sensing and running a lot faster. And if this is something that you'd want to see afterwards, and this is just using FMI to be able to be exported back into other tool sets, I'm more than happy to go deeper dive personally. If you're in the aerospace industry, maybe you're designing some, you know, turboprops, maybe you're getting some different scenarios. We were able to get you know, almost again 99.8% fidelity of our aircraft model, and bring down, you know, and get something going 90 times faster, right? So we only use 5 parameters, and that's a common question, right? What data do I need for my definition? How many inputs, how many outputs, right? It's all based on the use case as well, but you know, this really was a vast improvement of not only being able to run 100 more scenarios in the same elapsed time of running one in a system level simulation with extreme accuracy, right? So that's kind of the process of really why we wanted to leverage ROM in this use case, right? So you'll see that that was a 90 time faster simulation, but you almost have a 1-to-1 exact, right? Because of how well it was able to train and validate onto that system simulation, right? It was an amazing fit. So it was able to speed up our mission profile simulations and all of our simulations of our aircraft a lot more effectively. Right? We did something, you know, there was an EPA 5 thermal management analysis where we had, you know, a simulation taking, you know, over 300 seconds, right? We then, similar to what you just saw, right? We sped it up, incorporated it into the different drive cycles, kept that physics-based model, and got it running obviously a lot faster, right? So the main aspect, as you saw, or you constantly keep hearing, is reduced order modeling wants to keep the fidelity that you have in your model itself, but get it to run fast. But you want it to run fast but effectively, right? Meaning you have high training fidelity, high validation fidelity on your inputs and outputs, so that you can trust what you're running your simulations through as well. A lot of times people also talk about edge technology, right? So this IoT digital twin, executable digital twin, maybe you have a CNC sensor, right? Running these on the edge. So we were able to not only take the process of using Simcenter HEEDs, we optimized the multi-body, the chip sizes, the thermal aspects, as well as being able to deploy it and get real-time data on the industrial edge, running this reduced order model. And there's something called Live Twin that will really allow these executable digital twins to be deployed and ran simultaneously. And it will, if the sensor triggers an alarm, it'll detect all of the inputs of the data, run a simulation, provide that output. Or if you have it to be completely automated, it can then alter some various controller logic that you'd want it to change and get back to within the specs that you need to silence or get rid of that alarm. Another one, as you saw before, right? So we have these CFD type functionalities. Maybe we have different set points. So using, you know, interpolation ROM and the POD functionality, using those fields, we have the capability of really assessing and getting different temperatures on the fly, right? Which is a big deal when we know CFD tends to be extremely cumbersome in terms of CPU usage. Another one we did with CFD for engines, right? So getting that functionality and capability of converting a CFD design, we then used those parameters to define and train a neural network, extracting it, right? And it's really just amazing to say, hey, I have my 3D groups, my CFD groups, my controller groups, and we can all kind of synergize and work together if you can then validate and get these ROMs passed around, you know, ultimately to be used in whatever tool set you have, with the ability of Onyx, FMIs, AimSim if you're using it, right? That really allows just design optimization and exponentially a lot more effective solution. 2D fields also used here, right? For heat exchanger, CFD runs were ran, right? You see that we can still get that on the fly prediction functionality for those different designs inside from that reduced order model, right? We already went through and saw the validation of the bus bar, right? If we're doing aircraft cabin, right? Very similar. So we had a CFD run taking roughly 75 minutes each time, right? We know obviously CFD can be very cumbersome on the computer. When we then took that neural network or that CFD, developed a ROM from it, was a neural network, we then got it to go down to 0.3 seconds each time we simulated inside of AIMSIM. So we incorporated that reduced order model inside of a ECS model, and we ultimately got 15,000 times faster. So we are able to now run the boundary conditions, incorporate it with the environmental control systems, whether that's the fluid analysis or the aircraft mission profiles or the different controller logic embedded inside of it, and it ran in 0.3 seconds rather than that 75 minutes that it was in CFD alone. Similarly, we have the battery model, so you can discretize it. We had one that had ultimately a whole bunch of cells. We have a lot of these blogs from a Siemens standpoint that we've done with different organizations, but we're able to take this high voltage battery and get it to go from 612 seconds ultimately to a speed up factor of over 200 to get down to being 3 seconds, right? But still keeping that high training fidelity, and now having the ability to also incorporate and develop some level of a hardware in the loop or battery management system. Okay. If we were looking at electronics cooling, right? So this is an AIMSIM model. We then had complexity, but one thing here to point out is if you're using Simulink, right? We can use the FMI functionality, import that Simulink, and develop different controller logic. So we were able to take this FMU and speed it up to be about 1,200 times faster. Okay. Another factor you might be using if you want to export to a PLC, we talk about edge technology. There's different PLC portals that are embedded inside of our AIMSIM tool set. So it's called PLC Sim Advanced, right? Or it's actually ultimately PLC Sim, but it really allows us to do virtual sensing, hardware in the loop type functionality, because you're able to get your simulations to run a lot faster and effectively, right? If you were in the marine space, again, those 2D fields, predictions of wake from a propeller, right? You can also do that from a propeller of an aircraft if you were doing some level of simulation as well. So there's a lot of exploration, not only in these 2D fields from CFD, maybe we were doing it, as you saw before, from an FEA. The other one was temperature. This one's full acoustic based, where you can have kind of this 2D fields sweep of properties. And one thing that's being measured here is the IACC, so the inter-aero cross correlation, right? So the measurement of the difference between the two signals of ears of a person, right? So acoustics is a big deal when it comes to different pressure fields inside of a cabin. So one way to speed it up is using reduced order modeling. Okay. As I said, this was a new release, so there are some new amazing features. First one is there's this new interface, right? So there's a completely new rebranding from our Simcenter ROM builder tool. There's a correlation plot where you can see different data sets in all of one histogram scatter plots. We have those compilers that are all embedded inside of that tool, right? So if you're doing an FMU, AIMSIM, there's a GCC compiler. We have ways to also have other distributions of compilers. There's an integration to Teamcenter. So Teamcenter is a way that we have incorporated for modeling or management of data across an enterprise. And then the last is there's a lot more exploration embedded inside of Star CCM now, incorporating those 2D fields and really having that functionality, right? So if you see kind of this is the newer interface and that correlation plot that you'll get from the data. Okay. So I know a lot of that was a lot of information. There was a lot of demos. There was a lot of applications. But one thing, you really just have to keep in mind is, why did Siemens move in this direction? What does Simcenter Reduced Order Modeling offer, right? So ROM Builder now is Simcenter Reduced Order Modeling. It's this simplified tool. So hopefully you saw You can take data sets of CSV files, data files, AIMSIM files, CFD data, right? Process them beforehand if you wanted to, but you're really taking these and connecting these different domains in a very highly effective way. So you don't have to be an expert in this reduced order modeling techniques, right? So that's where you saw that automatic sweep functionality and capability. You have the user interface that tells you how well it was able to train on that data. You can have it from different data sources. So as I said before, it can be from tests, it can be from simulation, it can be from CFD, right? It can be from homegrown tools. And without having any prior knowledge, you can use the apps and wizard embedded underneath, but then it gives you these comparisons. It gives you the metrics on the training losses, how well it was able to validate the different plotting of, pre-processing, post-processing. And with one simple click of a button, you can export it, whether that's an FMI, AIMSIM, a Simulink S function, Onyx file, right? There's also other ASCII files that you can incorporate and do a level of post-processing scripting on. Okay. I'm more than happy. Here's my contact information. I'm more than happy for if anyone wants to discuss this further or reach out to Scott and the team. I'm more than happy to discuss a specific use case, or if you have data or further questions on the reduced order modeling techniques or what we offer from a reduced order modeling standpoint, I'm more than happy to have offline discussions. So I thank you for joining me today.
Terrific. Thank you so much, Darren. That was definitely a very rich presentation with a lot to absorb. We are running a little late, so I'm only going to make time for one of our questions that came in. And I think it's one that we probably all would have, having seen the presentation, which is, Darren, this almost seems too good to be true, to be able to get thousands of times faster results from a reduced order model, whether you got it from test data or whether you got it from a simulation. What's the downside? What are the warnings? Watch out for this, watch out for that. Putting inputs outside, for example, the range of the data that was used to generate the model. What sorts of things would you say to a new user for Simcenter Reduced Order Modeling to keep them out of the weeds?
Yeah, so that's a great question, and we get it quite a bit in terms of, how do we pre-process the data? How do we look at what types of simulation or design of experiments that we're performing prior to being able to import it into a reduced order model? So I wasn't able to show it, but there's a pre-processing functionality. So if you have some anomalies of your data, you're looking at it and you have some outliers, you can automatically remove those, then that will skew your training. What's really amazing too is in that model sweep, it's doing the different model order reduction techniques. So whether that's a Gaussian process, an RSM, right, so response surface model, maybe a neural network, maybe it's changing the different activations or the way the neural networks are defined. It's not only giving you the training or activation or training or validation fidelity, how well it was able to perform those techniques, but what's really great is it's going to extrapolate and be able to train so well that within that data set, you can have a level of expertise or knowledge saying, hey, I know that if I did a sweep between, let's say, 10 and 100, right? Any value between 10 and 100, I'm going to have high hopes, and that neural network or that reduced order model is going to give me almost 100% correct answer based on how well it was trained and validated. Now, when you get outside of those realms, that's where it gets tricky, right? So you're basically training and validating only on that data that you gave it. So if I put in a value of 200, right, we don't know how well that training is going to be with giving that output because it wasn't trained on that data. So it wasn't a specific input. So the problem there is we don't know what happens to your, let's say, thermocouple through that process, and it might, or even a battery, right? There might be some level of shorting that occurs through that process that we don't know because we didn't simulate it on. So it's all based on the inputs that you use inside of it. That's why I always say garbage in is garbage out. But if you do put in great data sets and you have a specific range that you're training and learning on, you're definitely going to get high fidelity data for that. Extrapolating it outside, it's all up to speculation because you weren't able to really, you didn't use it as a training set. Now, if you brought in and did more design exploration and got different inputs and had that broader range, then you'll have a training fidelity and validation to know, hey, maybe between the data that I got between 0 and 200, I know what my outputs are going to be because you were able to simulate it on or test on it and train on it as well.
Great, thank you so much. Thank you so much for your time today, Darren. It was a very fascinating webinar, very exciting new tool from Siemens. If anybody participating today would like further information, this is my contact information. Feel free to reach out to me regarding the Simcenter Reduced Order Modeling or any of the other Siemens tools. Thank you for joining us this afternoon for this ATA educational webinar series on Simcenter Reduced Order Modeling. Thank you for joining us.